So given the setup from the previous video, we are now going to use algebra to derive our mathematical model for our equilibrium expression involving our variables x and y as we defined them previously. So in order to do so, we're going to take our mass balance equations and solve for the concentrations in our equilibrium expression involving x and y. So first, we're going to start with MDH and use the MDH mass balance equation to get an expression for MDH free concentration. So in order to do that, to solve for our MDH free concentration in our mass balance, we're first going to subtract the copper 2 MDH concentration from both sides of the equation. So we'll be left with MDH free concentration is equal to the total concentration minus the concentration bound to copper 2. Now, in order to sub in our x and y variables, we're going to divide through the equation by the total concentration of copper 2. Now what we have, we'll come back to this first term, but this last term is exactly how we defined y. The concentration of copper 2 bound to MDH divided by the total concentration of copper 2. So this will be replaced with y. For this expression, the MDH total concentration divided by the total concentration of copper 2, we remember that the experiment started with a solution containing copper 2 bound to MDH. So this was a fixed amount, and because they are bound in a one-to-one fashion, the concentration of each of those in total will be equal. So in other words, this ratio will be equal to 1. So this is replaced with 1 minus y. Now let's look at NTA free in our equilibrium expression. So similarly to MDH, we're going to solve for NTA free by subtracting the concentration bound to copper 2. Again, we'll take the resulting expression and divide everything through by the concentration of copper 2. In so doing, we now have NTA total concentration over total concentration of copper 2, and that's precisely how we defined x. But we're subtracting something we don't have an expression for in terms of x and y yet. So we need to actually look at the mass balance equation for copper 2 in order to replace that with something. So as we see, we want an expression for copper 2 NTA concentration. So in the copper 2 mass balance, we're going to solve for that by subtracting the copper 2 MDH concentration from both sides. Again, we do the same step we've done before, divide each term by copper 2's total concentration. And now at this point, we recognize that here we're dividing the same number by itself. So that will be 1. And this expression is what we defined as y, the concentration of copper 2 bound to MDH over the total copper 2 concentration. So this is 1 minus y. And therefore, we can sub that in for our question mark, because that was our copper 2 NTA concentration over copper 2 total. And so NTA free's concentration over copper 2 will be x minus 1 minus y. So now we can take these expressions and we can sub them into our equilibrium expression. However, we need to do one more step before we do that, because every expression over here is divided by a concentration of copper 2. We need to divide everything here by a concentration of copper 2. So as you can see, we just took each expression and I've color-coded it to match our color coding of the x and y expressions and divided every term by the copper-2 total concentration. Because we have the same number of factors of copper-2 total concentration in the numerator as we do in the denominator, those would all cancel and we would arrive back at the original expression. So essentially this new expression here for the K exchange constant is algebraically equivalent to the original expression. And the advantage is now we can replace all of these quantities by what they are. So the pink corresponds to our 1 minus y. We found in green the copper-2 NTA is also 1 minus y. The NTA free in yellow is the x minus the quantity 1 minus y. Of course, I need a division and an equals here. And then finally, the copper-2 MDH over copper-2 total. That's how we defined y. So now what we want to do is we want to simplify what we have here at the top. Let me erase to get some room. Okay, so I have rewritten what we just derived, substituting in for the concentrations in terms of our x and y definitions. So what remains is to simplify this resulting expression here in order to get it in a format that we can then fit using origin. So what we want to do is we're going to first multiply both sides by this denominator so that we do not have a fraction in our final output. Next, what I'm going to do is I'm going to subtract the 1 minus y times 1 minus y from both sides so that we have all expressions involving variables on the same side of the equals sign. The last step I'm going to do is just some house cleaning. So I'm going to distribute this negative on the 1 minus y. And I'm just going to rewrite the 1 minus y as 1 minus y squared to clean things up. So this equation that I have now boxed at the bottom is our mathematical model for our equilibrium expression involving copper-2, MDH, and NTA. One thing I want to point out here is that there's no further simplification that can be done that would allow us to separate the x's from the y's. In other words, we cannot isolate y on one side of the equation and set it equal to just a function of x. In other words, what we are left with here is an implicit function because we do not have one of those variables isolated. But it's okay that we have an implicit function because the software program Origin can handle fitting implicit functions. So in looking at spectrophotometric data, right, we fix the x, that's our concentration of NTA, and we observe y, the concentration of copper-2 MDH. And so we fit this model using those x and y observations in order to estimate this constant equilibrium constant for this equilibrium reaction, and thereby we can solve the original problem of finding our equilibrium constant for copper-2 with MDH.